Alright, today I will talk about the problem pollutant control. So in this problem, we want to find the minimum cut, and basically what that means is basically see what is the minimum cost that we need to shut down the route so then we can't reach the final stop. And normally this would have been done very easily because the minimum cost for the cut is just the maximum flow, because you have to cut all of those flow off and able to stop this whole thing from flowing into the end. But here we have to find the shortest amount of pass required for this. So we have to find the least amount of edges required to cut this. And so it's a bit more complicated than usual, but the logic is actually really simple. So first, I will just create this new structure because we will use this later on afterwards. So this will keep track of an edge. This is the starting point, this is the ending point, this is the cost to shut down the edge, and this is the index of this edge because that's what we want to print out at the end. And so first we'll read in these inputs. Also, I will add this to our capacity, but this capacity has to be stored in a different array than our capacity when we get the maximum flow, because this will come into use later on. And so we'll just increase it by this much because we do increase instead of just setting it to equal to this, because there can be multiple edges from the same node. And then after we've got all the edges, we will sort them according to their cost. So we start with the maximum cost, and we do that basically in a greedy approach, so then we can always pick the greatest cost of an edge, and then later on we will be able to, since we can think of it as flows, because it's basically the same thing as a maximum flow problem, we can think of these costs as flows, and we want to get the maximum flow possible from one edge, because then we will be able to pick less edge afterwards. So I created this comparing function here to get always the greater ones in front. And here for each edge, we will try what will happen if we remove this edge from our graph. And so to do that, I will use this function called restore the capacity, because here, as I said, every time we'll try removing this edge and see what our maximum flow will be after removing this edge. So we will always change the capacity here in our maximum flow algorithm. So we will store this original capacity in this different array, so we can always restore it afterwards for each edge. And here's the maximum flow algorithm. I will use the Ford Fulkerson algorithm, and along with a little bit of Dijkstra algorithm, so we can get the maximum pass. And so this will be our main get max flow function, and here we'll keep on calling this Dijkstra's algorithm, and every time we call this algorithm, we will get the pass that has the maximum amount of flow possible, and this will just keep on going until we finally return 0. So when we return 0, this will mean that there are no more paths possible to the final node, which basically means that we've already used up all the maximum flows, and so this will stop afterwards. But while it's still reading that, we will always construct a path here. So this is basically a normal Dijkstra algorithm. We'll get the maximum distance that we didn't visit yet, and then set that node to visited, and also have to check if we've already visited everything, then we'll just do break. Otherwise, we'll loop through all of our possible capacities and check if there is an edge, or basically if there's a capacity from U to V, then that means we can flow from U to V. And also have to make sure V is not visited, and also have to make sure that this capacity that we found is greater than the current distance for V. And so what this does is that it will give it another maximum distance, because we want the max to make this flow as big as possible. So we'll change it to this and give this V a parent of U. So we will use this in a while loop to get the parents, and we can change the capacity later on. And then, so basically, if we cannot reach n, that means that we cannot have a path to n, and that will, so then the parent of n will just remain as default, which is -1, and so we will know when we have already filled up this plot. And so here's where we use the while loop to get the parents. So this way we can get the edge from this u to v, and this u is basically the parent of v. So here we'll get the minimum of all of these capacities that we used, so all of these edges that we used, and we get the minimum because we will decrease everything along this path by this minimum flow. We cannot get the maximum flow because then the maximum flow will exceed some of the capacities, and that would not be allowed. So use another while loop here, but this time decrease the capacities by this minimum flow, and also increase the residual graph of this. So then later on we'll be able to undo this. So what this undo basically means is that you can go back and change the direction of this flow using this capacity in the reverse direction. So from v to u instead of from u to v. And then finally, you add our total flow by this minimum amount of flow. And so this will go on in this Dijkstra algorithm, and we'll just keep on going until until this returns 0, and then we can return this flow. So we also used it here to get the original maximum flow. So this is the maximum flow without changing any edge. And then we will sort the edge, and here we will see what happens if we remove this edge from the graph. And so basically that is the same thing as taking away the capacity of this current edge from this u to v. And then here we get the maximum flow again. And now we check if our original flow minus the capacity of this edge is equal to our current new maximum flow. So if it is equal, this will mean that this edge was an important edge, and if we remove this, we will not be able to have as much flow as possible from the graph. And so this is what we want to do. We want to remove as much. We want to take off as much flow as possible. So we will just subtract this away from the original flow, and so this will be one of our answers because this actually did affect the overall graph in changing the maximum flow. So here we'll add over here outside of the loop, I will keep track of the sum of our capacity, and so when the capacity reaches our original flow, this means that we have taken away everything. Taking away all the flows with the minimum amount of edge, because every edge will have the maximum possible capacity here. And so if it's equal to that, we can stop this loop. And otherwise, if it's not equal, we will just look at the next edge again and see what happens. So we restore this capacity again into the original capacity, and remove this edge capacity from u to v, and get the maximum flow again, and just compare this again and see if this was an important edge. So this will just keep on going until we reach the original flow. And so after we reach the original flow, we will have everything in the answer, but here you have to sort the answer again, because here also we did a loop from 0 to n, but here we've already sorted this edge once, and so that's why I also kept track of the index of this edge, because it changes after we sort the edge array. And so here we sort this answer again according to the index of the edge, and we print out the size of this answer, which basically means how much edge we removed, and also we print out the original flow. And this original flow, as I said, it's the same thing as the minimum cut, and so this will be the minimum cost that we can get. So after this, we'll just print out all the edges inside this answer list.